moving like this, turning, obviously the rest of the arms will also turn, right? And about what axis will they turn? What is the axis? In this case, they were moving along about zi minus 1, right? Because the displacement was about this axis. How about in this case? Same, because the turning is about this axis. This is my axis. This is the positive direction. When it turns, the turn will be defined by that. So in this case, j omega I will be equal to zi minus 1. Okay. Now, will there be any linear velocity or no?
Yes.
Right? A revolute joint creates both angular and linear motion. So when this is moving, the point is turning. So this point will exactly move. It might move to something like this. Right? When it's moving like this at a theta I dot, right? So it can move like that. So when it moves, obviously the coordinates of the point have changed in some time. So if you differentiate it or divide it by that time, you get a linear velocity. So in this case, we need to find what is JV. Okay. So one thing that you should know is when you have a, let's say a joint like this is the length of the joint. And if you're tracking the point here, okay, and if this is turning at a rate of theta dot, the velocity, linear velocity, there is a relation between linear velocity and the angular velocity. So V will be equal to theta dot times R. Okay, omega R or theta times the R. So the longer R is, the faster it will have. The shorter R is, the slower the linear velocity. Okay, so in this case, theta dot we know. Okay, the angular motion, or I can write this as V is equals to omega R. Okay, omega is theta dot. So in this case, we need to know R. R is nothing but here, R will be equal to this distance, which is ON minus OI minus 1. Okay, this is vector subtraction. When you add this plus this, you get this. So if you look at this diagram here, let me write it like this. From here, you can say that OI minus 1 plus R is equals to ON. So you go like this, O is equals to ON. So I can write R as ON minus OI minus 1. So now we can say that JV will be a cross product. JV will be equal to the cross product of Zi minus 1, because the axis of rotation of theta dot is this, cross ON minus OI minus 1. So this matrix for a revolute joint will be equal to Zi minus 1 cross ON minus OI minus 1 divided by, sorry, not divided by. Okay, so these are two important matrices that you should remember to construct a Jacobian. This is for a revolute joint. This is for a perspective joint. Okay. Now, is this clear, or is there any part you want me to go over once again? Anything that you would like me to go over again before we move on to finding out ON and OI minus 1? So basically what we are trying to do is this j omega, obviously you have to understand that any revolute or any rotational motion will generate both linear and angular velocities. We need to know if there is a linear motion, about what axis it is, and if there is a revolute motion, about what axis. So revolute is obviously about this axis, because that is how it is defined. You choose an axis for theta I, which is the axis about which you generate motion. That is how we do the DH table. So that will be Zi. In this case, it has to be a cross product between Zi and the distance R, which is from this joint to the end effector joint. So it takes into consideration all the intermediate joints, because anything before that is not affected, only the joints after that. If I'm generating motion here, The previous joints are not affected, the consecutive joints are affected. So this will be ON is your final joint minus your current joint. Okay? All right. So how do we find ZI minus 1 and OI minus 1? The way we do that is when you look at the T matrix, which is, let's say, T0I, okay, T0I, which is A1, A2 till AI. Okay, so this will be equal to, I can write this as R11, R12, R13, R21, R22, R23, right, this is a homogeneous 4x4 matrix. This will be the final column here. This is OI, and this is ZI. Okay, this represents, this is the rotational matrix. When you look at the rotational matrix, this gives you the orientation of the z-axis. This is not necessary, but I'll write it. We don't use it. This will give you the orientation of the y-axis. This gives you the orientation of the x-axis. Okay, that is the origin of the frame. This is the origin of the frame. So you know where the origin is located. These three will give you how it is tilted in space. Okay, so at this point, you can have an origin like this, but it can be at different angles, right? It can be at the same point, but it can be at different angles. So this these values will define, these column matrices will define the orientation. So if you want to find ZI, OI, and so on, you'll find it from EI. So once you do this, it becomes a stepwise method to find the Jacobian. You don't have to differentiate the equations. You can straight away from TI, you can calculate ZI. Now, just for those of you who are not familiar with doing the cross product, if you have two vectors like this, A, which is AXI, AYJ, plus AZK, which is unit vectors, IJK, and B is BXI, BYJ, plus BZK. If you want to do A cross B, right? Obviously, this is once again not commutative. So IJK, you have AX, AY, AZ. So A cross B will be equal to in this case, you'll multiply like this, AYBZ minus BYAZ. Then you'll avoid the center one, and then there will be AX BZ minus BX AZ, and then AX BY minus BX AY. All right? And always remember that this is your A matrix here, and this is B. A cross B is not the same as B cross A. Okay. So let's check this. Formulation with the structure that we started with, which is the 2 degree of freedom structure. And let me list out the A matrices so you can work with me to develop the Jacobian. Okay, so you have a Jacobian of a 2 degree of freedom manifold. Okay, that's fine. Okay. So in this case, you have 2 degrees of freedom. T01 will be equal to A1, which is equal to sine minus cos T02 A1 A2 is equal to Alright, now you need to tell me what is the Jacobian in this case. So if you look at so you have, this is a 2 degree of freedom manipulator, so n is equal to 2. Okay, so J will be equal to J of Q will have J1 and J2. Both of them are revolute. Okay, so both of them are revolute joints. So we know that Ji of R is equal to Zi minus 1 cross On minus Oi minus 1 Zi minus 1. Right? So here we can say that for this manipulator, J of Q will be equal to, the first column, J1 will be equal to Z0, okay, Z0 cross, N is 2, so O2 minus O0, okay, I minus 1, because here I is equals to 1, okay, and here this will be Z0, 1 minus 1. Here you will have Z1 cross O2 minus O1 divided, I'm sorry, not divided by 0. So we need to find these two, okay? This is your first column of the Jacobian, J1, this is J2. So from here, we can say, all right, so this will be Z1, this will be O1, this will be, we don't need Z2 anyways, but this is O2. Okay, Z0 will be obviously the way z-axis is aligned. Z-axis is like this, so this is Z0, Y0, and X0. So we can say Z0 will be equal to 0, 0, 1, and O0 will be equal to origin. Origin O0 is the first frame, so we'll assume these, because O0 is 0, 0, 0, this is the first origin, and this. Okay, Try to do this and tell me what you get. Find the cross product, tell me what you get for the Jacobian. So if you look at, this column is already here, Z0 and Z1 are already given, so you don't need to find Z0 and Z1, you already have that. So here, Z1, we know, okay, let's take this one. So you know Z0 is equals to, right? And O2 minus O0 will be equal to, O2 is this A1 cos 1 . So that will be the same thing. It will be the same, exact same thing, which is so now what you have to do is you have to do a cross product, which is Z0 cross . Okay, that is Z0, and this will be okay. This will be negative. Minus of minus, so this will be plus. Do that for the second one and tell me, so here you will get J1 will be equal to right, that is J1. Tell me what you get for J2. So J2 here will be Z1 cross this. We know Z1 is from here. Z1 is right here, which is 0, 0, 1. O2 minus O1. O2 is the same, which is this. Minus O1, which is A1 sine 1. So this will be equal to A1 cos 1, A1 sine 1, 0. So O2 minus O1 will be equal to A2 cos 1, 2, A2 sine 1. Alright, so we need to do a cross product of these two, Z1 cross O2 minus O1. Set it up exactly like this here. So once you are given any DH table, you can easily calculate T, because you can calculate A, then you can find Ti of any joint, transformation to any joint, and then you can find Z0, O2, O1, and you can, computer program can generate any given Jacobian.
Isn't it minus at the second term of Z?
This one?
Yes.
This one?
Yeah.
It will be minus of minus. It will be okay. So let's say this part, right?
Yes.
Let's say this part is X, okay?
Yeah.
All right. So if you look at this, when you do the center one here, you write minus, right?
V close I, yes.
Okay. So this will be minus of
Okay, yes.
minus X. All right?
Okay.
Okay, so let's do this one. So this will be here, we will have I, J, K, 0, 0, 1, and A2 cos 1, 2, A2 sin 1, 2, 0. So tell me what do you get?
A2 cos 1, 2.
Minus.
Minus, yes. Minus A2 sin actually. Yeah.
Okay. And we know Z1 from here. We know this. And we know this. So we can write J2 as Z1 cross O2 minus O1 and Z1. So this will be a total matrix which is like this, minus A2 sin 1, 2, A2 cos 1, 2, 0, 0, 0, 1. So we can write this matrix here, which is J of Q will be equal to J1, J2, both are revolute, so this will be equal to the first matrix, first column, Okay, I want to give you a problem that I want you to find out here. We have a 4 degree of freedom manipulator, a 4 DOF SCARA arm, 4 DOF SCARA arm. So this, what is a SCARA? SCARA is a RRP arm. Okay, revolute, prismatic joint, and then again a revolute joint. So I'll give you the P matrices. here, so here you have, I hope. Okay. All right, so A1 is this, or A1 is nothing but T01, is exactly the same as the previous one. Okay. P02 will be equal to P03 this is -1, I'm sorry, so this will be -D. Okay, and finally you have P04. So this is rather long, so let me write it here. Okay, because this is A, R, R, P, R, and here you have J will be equal to okay, this is revolute, this is a prismatic joint and again a revolute joint. Okay, so here you can write this as the first one. For a revolute joint, this will be Z0 cross O4 minus O0, right? And this will be Z0. Then we go to Z1 cross O4 minus O1, and this will be Z1. What about a prismatic joint?
0 to
First one is JV, so this will be Z2.
oh yeah.
Okay? All right? So this will be JV, and here you'll have So this will be here. From here you can tell that this is Z4. You're not going to use Z4 anyways. This is O4. This is O3. Z3. Z1. O1. This will be Z2. Okay. The only thing that is left is what is O0 and Z0. Okay. O0 obviously is the origin of the base frame or the initial frame, which will be 0, 0, 0. And Z0 is assuming it's aligned in the standard way. So these two axes are the standard here. This is J1 of R, this is J2 of R, this is J3 of P, because it's a prismatic joint, and this is J4 of. Okay. I want you to practice this question because in the next class we'll have a quiz on the Jacobian.
Oh my God.
You have the whole weekend to practice.
We need some break.
All right, we'll put it on Thursday. Fine, coming Thursday. So we'll try to program this. It's obviously for very complex manipulators, you can't go on doing this up till a structure that has 6 degrees of freedom or 5 degrees of freedom. You should know how to do it by hand, and then you can program it. If you don't have the know-how of how to do it by hand, it's difficult to program. So anyways, we'll try to do this as a simulation lab. Otherwise, you cannot tie in the end effector velocities. You cannot map these two. Okay. So we'll discuss this a little further, but please make sure these columns will be singular. Mostly there will be unit vectors. You'll only have one